Okay, so JWST forms an image. We have a very classical Leo-style coronagraph with a focal plane mask and a Leo stop that is inserted into the optical path using a set of wedges that move the coronographic masks into the edge of the field of view of the focal plane array, as seen in sort of the middle strip. The bottom left shows the mechanical drawing, and the images on the bottom right show what the mask looks like with 1, 2 bars and 3 different sombrero type circular spots. I'll have more details on that in a moment. Each mask is made up of a large number of small, sub-micron sized dots shown on the right to build up a grayscale pattern that gives us our coronographic mask. So here's some more detail on the focal plane masks themselves. You'll see the 2 wedge-shaped bars, which give us the best contrast, the best inner working angle, something like 4 lambda over D, or 0.13 lambda. But you have to, of course, know the geometry of your system. You don't get a 360-degree field of view. But for working in as close as possible, the wedges give you your best choice on a known planet, for example. And, of course, you have to choose the role of the telescope fairly carefully to take advantage of that. There are also 3 round masks, circular masks, that work at 6 lambda over D, about 0.2 lambda inner working angle in arc seconds. And you also see top and bottom, the grayed in areas are neutral density spots that are used as part of the acquisition. The telescope will be put onto one of the spots, a centroid will be taken, that'll then be used to make a precision move into the appropriate place, either on the wedge, where there's a specific location laterally across the wedge at each wavelength for which it's optimized, or directly behind the sombrero. In some cases, we may use 2 spots, the bigger one and the smaller one, to get a still more accurate centering of the star behind the coronographic mask. Just to give you an idea of what the inner working angle translates into, of course, it's just dependent on wavelength. And here I plot the inner working angle, 4 lambda over D for the wedge, 6 lambda over D for the spot, as a function of wavelength, and give you an idea of how that might correspond to different known exoplanets. So some of the closest in ones, like 51 Erie, could be quite a challenge to do at about 0.45 arc seconds. As you move slightly further away, we can start to do quite a lot better in terms of being outside the inner working angle. So the Leo stops are shown here. There's 2 of them, one optimized for the wedge on the right, the other optimized for the spots on the left. And as you can see, the white areas, which are selected to avoid the cracks between the mirrors and to avoid the support struts for the secondary mirror, leave out a fair amount of the collecting area of JWST, with the result that the throughput's about 19%, which then has to multiply all the other throughputs in the NIRCAM system. It also leads to a fairly challenging DSF for any objects that are imaged through the Leo stop, and that's one of the challenges we will have when trying to find and characterize objects in the coronographic images. So this chart shows the coronographic capabilities with JWST compared to a number of facilities on the ground. So in light blue we have Mary, excuse me, that Pierre talked about, and you can see it reaches contrast of 10 to the minus 4 and eventually 10 to the minus 5. The dotted black line is NIRCAM at 4.4 microns, and you can see we reach a contrast of about 10 to the minus 5 at an arc second, and then we just continue to go out to very high contrast levels as we move out to many arc seconds. In between the Mary and the NIRCAM lines is a line in light blue, and that's an estimate of the performance of the L-band vector vortex coronagraph that Dimitri Maoué has recently put onto the Keck telescope for the NIRC-2 camera, and it has very good performance in close, and has quite a good contrast ratio compared to NIRCAM. But the important thing to recognize is once you get outside, about an arc second or so, 1.5 arc seconds, NIRCAM's great performance because of the low background of space takes over, and we can go down to much deeper levels than anything possible on the ground. The planets are brightest at 3 and 4 microns in particular. 4 microns is a very unpleasant atmospheric window from the ground, so the great power of JWST is not working in very close to host stars, but its great sensitivity to lower mass planets, and I'll describe that when I give a very brief overview of some of our observing programs. The other lines show what some of the ground-based systems can do. GPI, Sphere, eventually TMT or ELT can work into much closer inner working angles and high contrast, but of course they'll be limited by the Earth's atmosphere. Finally, in the upper left, we see the non-redundant mask of the nearest instrument that can achieve contrast of perhaps 10 to the minus 4 at a much smaller working angle than anything that either NIRCAM or Mary can achieve. So the following set of slides show the importance of the stability of JWST. JWST is not a spectacular telescope from the standpoint of its overall wavefront error, something like 130 nanometers, but it is expected to be highly stable. So shown here, some plots from John Christ show that at 2 and 4 microns, you get an idea of an array of sources at 10 to the minus 5 contrast, observed with a 10% roll to subtract out speckles, but the question then is, what is the wavefront error change between the rolls? So across the top, you see 1/4 of a nanometer change, 1, 5, and 15 nanometers of change. And you can see that all these sources, the little dots at 10 to the minus 5 contrast, are indeed very well picked out. If I go to the next slide, 10 to the minus 6 contrast sources become more of a problem if the change in the wavefront between one roll and the next is as large as 15 nanometers. You can see at the bottom right, F210 filter is really starting to be badly affected at 10 to the minus 6. And I should mention the little blue lines demarcate 2 arc seconds, 10, and 15 arc seconds separation from the on-axis star. If we go to 10 to the minus 7 contrast, you can see the effects of roll angle and wavefront drift become quite dramatic to essentially make it impossible to pick out sources if the wavefront error is large as 15 nanometers, and even at 5 nanometers of drift, it starts to become a challenge. And then finally, 10 to the minus 8 contrast level, we would be in fact very lucky to extract any sources at that level unless the stability of the system is considerably higher than we expect it to be. The best numbers we've heard is something like a 10 nanometer drift And so many of the things we've been doing with NIRCAM are based on that. There are also terms in the performance that depend on how well the telescope can center and maintain the centering of the star behind the spot. The models for that have improved somewhat over the years, and we're working to sort of update the calculations to take that into account. And that may make some of these plots a bit more optimistic. So there are a number of PSF simulation tools that are available from the Institute, and the website for those is shown at the bottom, and you can simulate the different levels of wavefront and different levels of aberration through the telescope. You can put in the different coronagraphs, and it provides a very useful capability for starting to model what you might see after an observation with JWST. You could add in your own wavefront aberrations, get a new PSF, subtract it, and be able to see what contrast level you can actually achieve. So just to give you an idea of an illustrative chronographic program, I'll lay out one that we're planning to do for the NIRCAM team, and then give you an idea of what the time required to complete that program would be. So one thing we're considering in a program that will be coordinated with MIRI is to look at 5 known planetary systems with a large number of medium band filters in both NIRCAM and MIRI, and try to cover the basic planet properties listed there. We take advantage of the high sensitivity of NIRCAM to go down to a few tenths of a Jupiter mass, and we select targets in an appropriate range of masses and separation. I won't go into a lot of detail, but with the filter set shown here, 4 or 5 NIRCAM filters and a couple of MIRI filters, we can recover planet properties relative to the input models that we used quite accurately. On the bottom, I show the sensitivity for deep searches going down to even a tenth of a Jupiter mass. Can be done quite straightforwardly at high signal-to-noise. We pick these objects out in 4 microns, and we can use 3 microns as a way to reject stellar extragalactic contaminants. We're also looking at an M-star survey. That would look at some of the closest and youngest M-stars with the hope of pushing down to still lower masses, essentially Saturn to Uranus mass planets, with the idea that if we work on the very closest objects, 10 to 15 parsecs, we're probing in the vicinity of the CO snow line, where you'd actually expect such planets to actually form. So again, we'd use a combination of long wavelength filters F44W and a shorter wavelength filter 322W2 to both detect the planet and reject the various outliers. Our plan here is to use the entire sample itself to help create the reference star library. I'll mention briefly, but I won't talk on it in detail, is of course there's great interest in using the coronagraph to detect disks in scattered light, using NIRCAM to complement the work that MIRI will be doing on disks. NIRCAM would also be usable to detect planets inside the rings that we see in many of these debris disk systems. So we try to image the disks both to characterize the structure and the composition of the dust, but also to detect planets. And because this diffuse emission is quite hard to detect, this will be very dependent, final performance will be very dependent on the stability of the system over several hours as we go from target to reference star. So one can use APT to define the program and to estimate the overheads, which are indeed, significant in a program like this. So taking the program I described earlier, where we use NIRCAM to look at 5 medium filters, which are fairly quick to measure the known planet, and then the 2 wide filters to go deep to look for new planets in the system. We perform 2 rolls. We look at 1 reference star, and then in coordination with Mary, I've put in some time to use 3 4-quadrant phase masks and 1 reference star for Mary. And you can see the sort of numbers that you get for observing times and the various overheads. So this is, the times here are optimized using what is called smart accounting within APT that tries to optimize the moves, the rolls, the instrument changes, and so on. These will certainly be changing. One could optimistically hope the overheads would get lower, but probably like taxes, they won't. So you can see we use NIRCAM on the reference star, we use the long bar, the short bar, the spot. We then do Mary on the reference star, then we go over and do Mary on the target, NIRCAM on the target star, and then the number of filters, the amount of time in minutes for the science observation, the instrument overheads. The initial slew takes approximately 15 minutes to get to the reference star, and then lower down, also in red, to go over to the target. There's some observatory overheads, and then the total time. And you can see that overall, the efficiency is something like 50%. And to do 1 target has taken something like 15 hours in the sequence of 2 instruments and about 10 different filters with rolls and reference stars. So it's somewhat sobering to realize it takes quite a while, even with a cold telescope in space, but one will be getting, we hope, very unique looks at these planetary systems. There's pipeline processing being developed at the Institute based on the HST experience. This is a chart from Remy Soumer where they were able to use libraries of PSFs to do much better than the original NICMOS processing after doing various processing steps using Loki and CLIP. They're actually able to extract multiple planets from this system here, both planets themselves and disks as seen below. So I think that will be relying a lot on the power of the pipeline processing being developed at the Institute, plus of course what members of the team and the general community will bring in particular as the library of PSFs is built up. So to conclude, the NIRCAM chronographic capabilities are limited by the as yet unknown stability, I think is the key word, of the telescope wavefront. It's large by the standards of extreme AO or future observatories like WFIRST, but JW should be highly stable, which offsets some of the disadvantages of the high wavefront, and working at the long wavelengths, we have an enormous advantage over ground-based telescopes. As I mentioned, the acquisition overheads, just general observatory overheads are significant, but APT and the new observing time estimator tools will help with the observation planning, and we expect that the Institute will provide both a PSF library that grows as the mission proceeds and advanced data processing. So I'm happy to entertain any questions.
Thank you.